Yeah, it's recording. Okay, perfect. Excellent. Okay. All right. So now that we are in business, it is my great pleasure to present Dr. Bogdan Suceava, professor of mathematics at Cal State Fullerton and many other things, mathematicians, writer extraordinaire, and our friend with a wonderful talk. So I'm already setting him up. He can only go up from there. Geometric inequalities between intrinsic and extrinsic curvature invariants. Welcome, Bogdan.
So thank you very much for being interested in this topic, and I would like to thank especially to Mihail and Andrea Bozian, because this topic has been discussed here for so many years. We had a couple of projects together about these particular topics, and we'll get to them in a few minutes. What I'd like to start our conversation with is motivation. It's at the same time historical as geometric. It's a work written by Chern back in 1968, and I don't think it's one of the most read works from Chern's heritage. So what I like to do is to actually get in the text and we learn how to read between the lines. Namely, we're at page 13, and we have the following. The rigid tensor of a minimal submanifold in the Euclidean space is negative semi-definite, and by the way, I feel like we should go through the proof of this particular line. We want to see why this is happening. And then, in the remark, he says the following. A minimal submanifold is, according to the above, an isometric immersion of the Riemannian manifold by means, if it's harmonic functions, right? Necessary conditions, so necessary conditions for such an immersion to exist are two. First, that M be non-compact, and secondly, the rigid tensor of M be negative semi-definite. We're going to be concerned with number two. Further necessary conditions are not known. Now, the subtle part is in the further necessary conditions are not known, and that's homework for us all to find more if there is more to be found. This is what we're looking at. I mean, reading Chern, it's actually, you can find inspiration in such remarks like, well, I don't know more than that. And on the next page, a related problem, so again, I'm reading from Chern. A related problem is the differentiable immersion of a non-compact Riemannian manifold by its harmonic functions. And then he's adding at the end of the paragraph, I do not know whether there is any condition on the given Riemannian metric of M. Now, this coming from Chern, this is very serious, which means, can we find more? So basically, you want to start with a Riemannian manifold on which you have a metric, and you want to find out conditions about this metric to control a possible minimal immersion into some ambient space. Here the conversation is about the Euclidean space because we are in the aftermath of John Nash's embedding theorem. So this is 1968. The theorem, Nash's theorem, went out in 56. It's the first decade after, and there is much to reflect. So given a Riemannian manifold, can we embed it into a given ambient space? Now the problem goes back to the beginning of the 20th century, actually to the 20s, when Eric Cartan and Maurice Janet worked on the immersion problem, and so it took about 3 decades to have a proof for the embedding theorem. And there was a lot of hope that once we can regard the Riemannian manifolds as subspaces, I mean submanifolds, into some Euclidean space, maybe there's going to be an easier access to information, either geometric or analytic or topological. That was the hope. Nash's embedding theorem, it's about this. It's about this hope. Every Riemannian manifold can be isometrically embedded into some Euclidean space. Now, we can also ask, what is the best possible embedding of a Riemannian manifold into the Euclidean space? And of course, the question is best defined with respect to what? Is minimality the best possible embedding, or do we have any further restrictions that could provide more insight into the nature of space? This is what we're discussing about, is the problem of space, the nature of space. So let's play a little bit. Let's go back to, can I call this a ninth grade introduction to the question? Because the algebra we're gonna need is very elementary. It's just for us to build some intuition into this process, okay? So what we have is a surface in R3. And on the surface, we have a point P, the tangent plane to the surface, and the normal and point P. And we consider all the normal sections, that is, the intersections of planes passing through the normal, going to the point P, okay? And the intersection of such planes with the surface. And we get a class of curves. These curves have a curvature of a planar curve. We're interested in the smallest and the highest value of these curvatures. Let's call those kappa 1 and kappa 2. So let's say kappa 1 is the smallest possible curvature of these planar curves, and kappa 2 is the highest. Now the Gaussian curvature is the product, kappa 1 times kappa 2, while the mean curvature is the average. Okay, so they have been introduced, the first one by Gauss in 1827, and the mean curvature by Sophie Germain back in 1831. So, for all the geometric quantities, we're interested in this distinction, if they're either intrinsic or extrinsic. Now, if we're reading the original, Gauss is not using the word intrinsic. He's talking about developable surfaces. He was interested whether, for example, if a part of a sphere can be developed, because he was interested in the problem of maps. He was interested whether a part of sphere can be represented on a map on the table. So that's like what, an isometric immersion of a surface into R2. And the short answer is no, because kappa is the very abstraction to it. So how do you prove that? If you can express kappa in terms of the term of the first fundamental form, that means that kappa is intrinsic. That's the geometric representation of the whole situation. So this distinction within intrinsic or extrinsic, that appeared later. Okay, but it was in Gauss's view, and I'm pretty sure that if he had the tools of topology, the language was the one we're mentioning today. So anyways, for us, intrinsic are the measures that are depending on the geometry of the subspace, and extrinsic, the measures that depend on the geometry of the ambient. Egregium's theorem states that kappa is intrinsic. That's Gauss's calculation. And Sophie Germain's insight, she claimed that that's not enough to characterize the shape by using just kappa, so that the mean curvature is also needed. And arguments were coming from physical considerations, and of course, the mean curvature being proportional to tension, she got it right. She has something called the law of distribution of curvatures around the point, and she's arguing for physical reasons that this is important as well. So kappa is intrinsic and H is extrinsic. That's the conversation we have. All right, back to the ninth grade. So let's go around with kappa 1 and kappa 2. How about kappa 1 minus kappa 2 squared? That cannot be negative. So if we rewrite this, a FOIL, and group the terms accordingly, then we got that H squared by very basic algebra is more than kappa. Now let's start reading everything and color code extrinsic and intrinsic like this. Let's use orange for intrinsic and blue for extrinsic. And I'm going to try to be consistent in the next few minutes with these colors, because there's going to be more than that. So now, why is this important? A surface in R3 is minimal if at any point the mean curvature is 0, right? So if we got that H squared is more than kappa, then we have an obstruction to minimality. If we find one single point where the Gaussian curvature is strictly positive, then H cannot vanish. All right? If S is compact, if S is a surface in R3, if S is compact, then there exists a point B so that the Gaussian curvature is more than 0. That requires a proof. It's a Morse type argument. Takes a couple of paragraphs of careful argument. But based on the above obstruction, we just proved that a compact surface cannot be minimal. This is actually consistent with what Chen was pointing out as a topological necessary condition. So For the geometry of some manifolds, the following problem is key. Find out simple relationships between the main intrinsic invariants and the main extrinsic invariants of the manifolds. And actually, we're gonna have a conversation here about various classes of inequalities that can be generated. And we're gonna pay attention what term is what, like what color should I use, orange or blue, when I start painting the terms. So we're working with these distinctions. And what we deal here with is characterizing immersions in the spirit of the Riemannian consequences of Nash's embedding theorem. That's the business we're in. Okay, now the main curvature invariants, let's discuss. The sectional curvature was introduced first by Bernard Riemann back in 1854. It was when he introduced the definition of a manifold. He also had this description of sectional curvature as being the natural extension of Gaussian curvature to planar sections in that manifold. That was Riemann's construction. And then, suppose we are in a Riemannian manifold M, endowed with a metric G, and consider an orthonormal basis U1 En on the tangent space at a point, at a given point, pointwise, on the tangent space TPM. Then the scalar curvature is the sum of all the sectional curvatures calculated on the N heater.
Hey, how are you?
Now, we're gonna denote by H the second fundamental form, and the definition of minimality naturally extends to submanifolds, and the immersion is called minimal if the mean curvature vector field vanishes at every point of the submanifold. Now, if we're gonna look in the general context, if we have a submanifold of dimension n in the Riemannian ambient space, and if the codimension is m, we're gonna have several relations where we hope to get this distinction very clearly stated. The first one is the Gauss's formula, which is actually teaching us how to compare the natural derivative in the ambient space denoted by nabla bar. There's the Riemannian connection on m bar, and the Riemannian connection on the subspace. That's just nabla. And the difference between them is a tensor. That's the second fundamental form. And a key element in this bridge between intrinsic and extrinsic quantities, the so-called Gauss's equation. All these elements with bar pertain to the ambient space, and the ones without to the subspace. So everything between intrinsic and extrinsic quantities seem to be passing through this bridge, this relation. And one may wonder, can we avoid it? Why avoid it? Because everything has been exploited in terms of Gauss's equation, but are there any other examples of relations between intrinsic and extrinsic that are not going to Gauss's equation? That's actually another important thought, and we're gonna reflect on this in a few minutes. All right, so we're just mentioning that Gauss's equation is the bridge between intrinsic and extrinsic quantities. Now, a particular case of using Gauss's equation is a calculation for the sectional curvature of submanifold in the Euclidean ambient space. It's exactly the setup for the Nash's embedding theorem. So what's going to happen is that in the Euclidean, this term vanishes. This term is gone. So this term here is here, while this other term goes with minus, and that's important, and it goes in here. So what we're going to do, we're going to investigate what happens with the Ricci tensor, and we're going to introduce this important character of the play in here on the next slide. What happens with the Ricci tensor for some manifolds in the Euclidean space? That's exactly we're following in the steps of Chern's remark. Right? I'm still spending time to explain those paragraphs in Chern's work. Right? So take a unit vector at point P. Now consider the completion of V to an orthonormal basis. Now, what's going on with the Ricci tensor? So Ricci tensor is the sum of the sectional curvature of all the faces that are actually incorporating the V. That's what's going on. So let's use the Gauss equation in calculating Ric 1, 1.
Okay.
All right. So by the first equal sign is the very definition of the Ricci tensor. Here is the Gauss's equation. Nothing new. We carry the sum, careful with the indices, is from 2 to n for both sums. All right? And then, here's what we're going to do. We're going to move this sum inside. That's the only move we make. Okay? And then here, there's one term missing, the term corresponding to H11. We're going to add it and subtract it. Because when we add it, we got the trace of H. That's going to be n times the mean curvature. And here, we just got G H11 dot itself, right? And that could go very well. It has a minus up front. It could go with the sum at the end. No problem. We just got here G H11 dot NH. And here's the remark. Now we're looking at the last line because this was just a very simple manipulation from linear algebra that happens pointwise. If H, capital H is 0 for minimals manifolds, then the first term cancels. So what we ended up with, it's a sum of squares with a minus up front, which means that this tensor can never be positive. This is what Chen was saying. Aha, good. So all it takes is just a little bit of clarification of ideas. So the Ricci tensor of a minimal manifold in the Euclidean ambient space is negative semi-definite. That was the argument. Good. So Chen wrote that Ric strictly positive yields the only known Riemannian obstruction to minimal isometric immersion into Euclidean space. And the point is, you're doing a calculation for intrinsic quantities, and you can tell something about the behavior of the immersion into some Euclidean ambient. That's good. Okay. So it's important to understand the Riemannian obstructions to minimality. You want to find out those Riemannian answers through intrinsic calculations. Or if you could characterize our classes, why not? Let's see how far can this go. So the problem is this. When does a Riemannian manifold admit a minimal immersion? That's a PDE problem. Or does not admit, and then this is a Riemannian problem, into an Euclidean space of arbitrary dimension. This is what we are looking at. Aha. And of course, if we really want to use this hope that was Nash's embedding theorem, then we should be thinking about intrinsic answers. Back in '93, so that's what, 31 years ago, Bogdan and Chen proved an inequality about, so the conversation there was calculate the infimum of the sectional curvature when you're at a point in a submanifold living in a space with constant sectional curvature. That was the beginning of this conversation. And of course, this estimate comes in terms of our Riemannian measures. Scalar curvature, curvature vector field, sees the sectional curvature in the ambient space. Okay, let's reorganize this information. As we promised, extrinsic versus intrinsic. Maybe just like this. Aha. So here's what's going on. If we are in the Euclidean ambient space, this quantity vanishes because little c is 0. So again, there is some control over the behavior of H, and this control is ensured by this quantity. Now in real life, to calculate the infimum of sec could turn into a computational nightmare because it's about getting the best basis and giving you all this. So sometimes you may be very satisfied with getting an estimate. And I believe I complained a long time ago about this in another talk that I gave here at Chapman. So thank you for that talk as well. Because getting that infimum of sec, that should be an Olympic sport. It's difficult. Okay, so what we're interested in is something that we propose to call them Bogdan type inequalities. That is, inequalities between intrinsic and extrinsic quantities that are characterizing immersions. That's interesting. So it all started in '93, and this is what we want. Not only that, but we want to find what kind of natural geometric conditions could generate such relations? That is the question. So it is natural to look at the quantity scal minus infimum of sec, because it naturally isolates itself in that term that we can paint in orange. And by the way, after that, in the last 30 years, there was a whole research direction. Now we have a nice, beautiful survey in the shape of a 500 plus pages book written by Bogdan and Chen, where all these results are collected and classified accordingly. But there is more to that, so that's why I'm thinking that, this is still alive and of interest. And this is so fundamental that, the proof relies on the following lemma that I believe it was used to generate inequalities back in 1973. I think it was used for the first time. And if this was, I don't know, the Putnam seminar, I would ask, how do you solve that? Well, it's a Cauchy-Schwarz with the one trick. The machine that's generating the inequality is, you may wonder, what if it's not Gauss's equation? Because you have used Cauchy-Schwarz and is this generating? No. We still have to go through Gauss's equation. Gauss's equation is here. So basically what you're doing, you're blending in Cauchy-Schwarz with Gauss's equation to generate the inequality. That's the proof. And I'm very careful about the tools because this algebraic core is actually generating the inequalities. We're looking at the inequalities. Good. So Gauss equation plus Cauchy-Schwarz yield for a submanifold in a space form of constant sectional curvature C, an inequality of the type we're looking for. And by the way, how many applications, direct applications of John Nash's embedding theorem are? Because there are few. Okay, one more time. There was a magnificent problem, rumored to be the hardest problem in mathematics, and John Nash solved it with the hope of making our lives easier when we calculate things about the nature of space. And what are we doing with it? Not too much. And the reason is that there are very few relations between intrinsic and extrinsic. And we are complaining that there are few. Aha, good. So let's look at this and let's see, can we get more? But back to Chern's question, obstruction to minimality. If, as we had kappa Gaussian curvature strictly positive or Rick negative, non-negative definite for arbitrary submanifolds, if there exists a point P on the submanifold so that the delta introduced here, described here on the left-hand side term, is strictly positive, then M cannot be minimal in R2 And this was a stroke of genius back in 93 by Chen. Okay? And that's an answer to Chern's question from 68. Good. So the study of the intrinsic curvature invariants pursues this noble heritage. And let's see what else can we say about it. So the main reference is the monograph I was mentioning, written by Bogdan and Chen back in 2011. So I have 2 hours, right? Just kidding.
Yeah.
So we can also talk about the scalar curvature of subspace in TPM. Why not? So we take a linear subspace of TPM, we create orthonormal basis there, and we add all those weights on the faces of the n-hedron. Here's the dimension R, R-hedron, where the weight is coming from the Riemann-Christopher tensor. And that's the scalar curvature corresponding to that subspace. Now I'm going to explain the most general Chen inequality. Consider the k-tuples n1 and k with kappa more than 0 satisfying the following conditions. First, n1, so it's actually a splitting of the linear space TPM into subspaces satisfying the following dimension conditions, n1, n2, and k. n1, at least one of them, of course, strictly less than n. None of them 0 or 1. And their sum does not exceed the total dimension of the space. For each such k-tuple, we can consider the following construction. Take the scalar curvature and then subtract out of it the infimum of the sum of scalar curvatures on the linear subspaces, which are mutually orthogonal, like we had perpendicular planes, right? And with that, these deltas are called today Chen invariants, under the understanding that for kappa equals 0, the Chen invariant is the scalar curvature. Taking into account two combinatorial constants, I'm going to call C and B respectively, then the following inequality holds true. We have the delta quantity, which is intrinsic, can never exceed an extrinsic quantity. That depends on the following. On the sectional curvature in the ambient space. So that's the very Riemannian structure of the ambient space of where you're sending the immersion. And the magnitude of H squared is the mean curvature. So this is the whole extrinsic arsenal with which we can compare the intrinsic DNA of the subspace. Okay, so that's the most general inequality known so far. And the interesting part is that these delta invariants are independent from one another. So basically what you have is a Riemannian manifold with a metric on it. And out of this, you can derive the Riemannian connection. Based on the Riemannian connection, you are constructing the Riemann-Christopher tensor, which yields the sectional curvature. And based on the sectional curvature, you can build the scalar curvature. And out of it, you're going to have your delta invariance. There's a whole DNA structure of that space. There's a whole structure here. And what are we interested to have a conversation about are the possible abstractions to minimality, because this was the beginning of the problem. So if H is 0, if one of the deltas exceeds the value of the combinatorial constant multiplied by the value of the sectional curvature in a given space form, then you cannot have a minimal.
What epsilon is positive, strictly positive?
Actually, it could be you think of a pseudosphere, could be negative as well. This works like a charm. No square there, promise you it works. That's actually interesting, you know, when some quantities can be negative, you can still have obstructions. Indeed, you can do.
Because, of course, in the case of a surface.
Back to the original. Look at this. Look at inequality. Okay, so what you're looking at is if this vanishes, if the inequality is backwards, then you cannot have a minimal immersion. That's the deal. Okay, in particular, if delta is strictly positive at one single point, then M admits no minimal isometric immersion into any Euclidean space for any codimension because the Euclidean space has sectional curvature constant 0. That's how it works. A few years down the road, Magnesium proved the following inequality. So the normalized scalar curvature is like when you're dividing scalar curvature by n choose 2. That's what's going on. So if you're comparing this manifold with the curvature in a space form, constant sectional curvature epsilon, then you get that this normalized scalar curvature cannot exceed h squared plus epsilon. This is like very natural, and it kind of gives you a feeling that we're on the right track here. This is so beautiful because, again, in the left, something intrinsic, in the right, something extrinsic. And it's very natural. It really, if you let epsilon to be 0, please.
One color. You forgot to color them.
I forgot to color them. I definitely, guilty as charged. I should have. Like,
if you want to grab a chair also, you don't have to stand because you're not writing on the board. It's right there.
I'm fine.
Okay. Good.
I can still hold on for a few more minutes. Should another relationship between intrinsic and extrinsic quantities, and that's the point. So, what's going on? Because all these quantities have been known since the 19th century, right? But that's a different way of thinking. After we understanding here, everybody interested in geometry, yeah, please.
Just one question. This one and the one before, they're not equivalent.
No,
They're totally different.
They're totally different. We have.
Okay. So there's no like hidden thing that they could be equivalent in.
The delta invariants are independent from one another.
Okay, great.
This is about the scalar curvature, which corresponds
Just making sure that.
Yeah, we have a package.
Great.
It's the DNA of shape. Actually, it was this beautiful paper. I think was written like in '98 by Bogdan Chen, where he's talking about the DNA of a Riemannian structure, because there are so many that it's actually characterizing. It encodes the whole information about this. And exploring this thought, what if you have a hypersurface in manifold with dimension n+1? this was actually something that appeared back in the day in my thesis. And I want to tell you what I was thinking about a few decades ago. I'm embarrassed to say when. It's about 99. Yeah, we won't mention it. So the whole point was, how about using something else as a generating machine, not necessarily Cauchy-Schwarz. Because if you have a real polynomial with all roots real, like for example the shape operator for a hypersurface, then by using Rolle's theorem, you can prove something about the quadratic behavior of the end of the derivative of order n minus 2. That was the argument. And what's in it? Well, if you're looking at the shape operator as an argument and using the Viet's formulae, I don't want to spend too much time here because I think this is quite related to what I said before, except that this number 7 should be explained carefully. This is Gauss's equation. This is Gauss's equation. So what I'm doing here, I'm combining again an inequality, that's an algebraic inequality obtained by Rolle's theorem, with Gauss's equation. So the mix is the same as in the previous inequality. And then you add them up and you obtain the claimed inequality. So 2005, two papers appeared at the same time, one by Bang and Chen, one by Koji Matsumoto and his collaborators. Same inequality appears there with good control over the equality case for arbitrary codimension. And the interesting part is the obstructions to minimality. What I found in 99 was this. If the scalar curvature of M is greater than the scalar curvature of every n-planar section in the ambient space, then M means no minimal immersion. So it's again this game between intrinsic and extrinsic. And the other very good point is that if the intrinsic scalar curvature of M is greater than the extrinsic scalar curvature, then M means no minimal immersion. Okay, good. Now let's change gears. What was that, 9th grade, 11th grade? What do we do? So in 84, this is actually quite well known if you have played with inequalities since childhood. Some people did. So in 1984, problem 1 was like this, was a constrained inequality. If the constraint is you have non-negative real numbers, A, B, and C, A plus B plus C is 1, then the following double inequality holds true. I'm not going to look over the proof. I'm not going to do that. What I'm going to do is something else. I'm going to turn this into a Chen type inequality for hypersurfaces. Why not? So let's see. What's intrinsic, what's extrinsic? And for that, we're going to have a more intimate conversation with another book that we read with pleasure when we were kids. All right? I mean, namely, is there any geometric interpretation to this assertion? If this can be interpreted in the spirit of what I said before, then you know what we have here? There are many answers to the question that Xing Chen asked. Right. That is the point. For a geometric interpretation, let's imagine a hypersurface En R4. Why not? Because I'm planning to identify A, B, and C with the principal curvatures, as we plenty have done in the previous slides. Okay, so that, and
Hey, you jumped too fast.
maybe, but I said it. So the whole point is that sectional curvature is the product lambda and lambda J.
Okay. Don't worry, because I have your talk right here.
Yeah, so I'm still trying to tell you everything I know in 1 hour. You know,
That's not possible.
so what is intrinsic and what is not? Now, with great pleasure, we're going back to Kobayashi and Nomizu, a book that will, you know, forever be in our hearts, because, you know, this is what we, and the question is, what is intrinsic and what not? And for that, let's take a look at, in the chapter 7, it's about submanifolds, and there is a whole big section about the behavior of hypersurfaces. And for the hypersurfaces, we have this characteristic polynomial of the shape operator. And curvatures are appearing as the symmetric polynomials. And here is this important paragraph. Observe that lambda 1 and lambda n are determined up to a sign common to all of them. Okay, this has to do with the choice of the normal. Think of the Möbius band. It could happen for hypersurfaces as well. Can you choose the normal now? What's the choice of the normal and so on? Now, this means that kappa with odd index that will determine up to the sign. Okay, bad news, extrinsic. While the ones with even index are defined uniquely intrinsic. That's the generalization of Gauss's egregium theorem. It looks like very natural to, aha, good. So we can think in this way. And then sectional curvatures are appearing as the characteristic values of the curvature operator acting on planes. These are like planes, right? Aha. But this depends only on the nature of the metric. So see, these products are intrinsic, although the eigenvalues are not. So the answer is in comparison. Omizu very clearly stated how to think. So we have to think in this way. All right. So this glues back to the the spring of '91 for us, if we took Riemannian geometry in the same time. All right. So point is back to the IMO problem. When we're seeing the sum, and that's in the restriction, that has to do with H. When we're seeing the product ABC, that has to do with the Gaussian with the Gauss-Kronecker curvature. All right. While this symmetric product AB plus BC plus EA matches the definition of the scalar curvature that we elaborated on in the previous slides. All right, so identify A, B, and C with lambda 1, lambda 2, lambda 3, and remember, that was for strictly positive numbers. What does it mean for hypersurfaces? It means strictly convex. All right, that's quite strong. We're having a conversation about something that looks like a football. It's a three-dimensional football in R4, all right? And the statement can be rephrased like this. If in the neighborhood of a point P on a, do we prefer strictly convex or convex? I'm going to call it convex, but I mean by this strictly more than 0, right? Convex three-dimensional hypersurface, the mean curvature is constant, namely it has to be 1/3. Then we have exactly this inequality. Let's paint it again. Okay, now it can be tough to prove such statements. I mean, some of them may be nasty. But the short answer is, there is actually more to it.
So is that 7/27, even from original problem? Is it optimal?
I don't know, because what I heard is that it can be improved. But again, what I'm interested in is how many inequalities do you have?
Okay. Because it comes very unnatural, the 7/27.
I know. Yeah. It also bothers me what is the general statement. I didn't think about this in this term yet. What I'm interested in is that the conversation is, can you have more? Then the set is non-empty. You don't have to go through the Gauss's equation, good old style. I mean, the only way you're actually using Gauss's equation in your interpretation. When you're saying the skull is that symmetric polynomial. What?
Just was saying that he has a copy of Kobayashi and he's 5 feet away from him on his couch. So that's
so my answer to this is that if he was that the Fahrenheit 41 movie, okay, I'm volunteering to learn it by heart because it's easy, So yes, good. Sleep on, yeah, please.
The
Volume 2, I prefer volume 2.
volume 2, okay.
He has a chapter on manifolds.
But
Yeah.
to actually answer that question, that less than or equal, then it should be, because otherwise, I mean, think about it. You have a case when that's,
It's not that easy. Even if your case.
I think it's
with
optimal. I think it's optimal.
Do you remember the 11/8 conjecture?
Yes.
Okay, so
Yeah,
that
that's true.
number,
Mhm.
can you find something that?
No, I'm thinking, no, in the Math Olympic problem, it's optimal. In here,
How?
maybe less.
I don't think so.
Okay, you know what?
Sorry.
It doesn't matter now.
I didn't really think hard about this part.
Mhm.
What I care about is just this interpretation. And
No, that's fine. That's great.
I was looking for something, everybody was looking at this now. What I'm saying is, let's look at this in the spirit of this invariance. Then there is more to say. Okay, so I'd like to thank to our masters, Tadashi Nagano, Kentaro Katsumino, for teaching us how to think. All right, I had to do that. Okay, now let's scale back and go back to 1855. When Ossian Bonnet was investigating the behavior of geodesics on surfaces. The paper with that generated what became later the Gauss-Bonnet theorem was written in 1844. This is the paper that generated the so-called Bonnet-Myers theorem. And what's going on here is the following problem. How do geodesics behave on a surface in relation with curvature? Now, with curvature, if you're looking at this, 1 over r, r prime. This is sectional curvature, or if you want, Gaussian curvature written Bonnet style. R are the radii of curvature, and that's like, I don't know, lambda 1, lambda 2 for us.
Right.
Right? That's what it is. So what's going on is a condition on curvature and in correspondence with a differential equation. That's very profound. It's 1855, and Bonnet is putting in connection the behavior of geodesics and curvature conditions. Okay, so we're going to call this the Bonnet condition. It's actually the one that was used by Sumner Myers back in 1941, instigated by Hans Hopf, to find out topological consequences of curvature conditions. The connection between curvature and topology, that's... so this is the original, really. Okay, so let's do this. That's a brand new paper that I wrote with my former student, Chern, who's right now heading over to UC Santa Cruz to his PhD program. So suppose you have a smooth hypersurface with sectional curvature bounded below by epsilon. That's the Bonnet condition. Then the following takes place. And all I'm going to say is, let me paint it in orange and blue, and you can enjoy it, which means that we have more relations like this. Now, how hard is it to obtain? And I'm going to tell you this. This is like 1 plus 1. Yeah, please.
There's also pink. So you put
What is the pink? Okay, what are we doing with the
condition.
What are we doing with the Bonnet condition? How do we regard this philosophically? And it's honestly, I feel like distinguishing it with a different color. What does it mean? So when you have sectional curvature bounded from below, if that is more than 0, then you force that to be compact. It's like I'm a problem. I'm doing fine tuning on ellipsoids, not ellipsoids. Something that's in the happiest case is looking like a football. Otherwise, it's just bounded away from 0, but compact.
So, we put to rest the problem. Jess is also saying that it's optimal. So we have 2 mathematicians against 1.
No, yes, but
The ABC,
why?
yeah. Because of the.
I didn't say it's not, but I said why.
He has a proof using the degree 3 polynomial. So.
Okay,
Anyway,
no,
so
I
that-
believe it
yeah.
exists,
Okay, good. Yeah.
I didn't say it's not.
Okay.
Mhm.
All right. So what I wanted to say about this theorem is this: what can we do more with these inequalities? I mean, because we have ways of generating them.
Bogdan, just one question.
Yeah.
How is epsilon cubed showing up there?
Can I go over the proof?
Okay, please, yeah.
Oh, sorry, I cut the proof for time reasons.
No, but just why epsilon
by
cubed?
foiling.
Oh, okay, okay.
By foiling, you have 3 conditions. You have 3 conditions about sectional curvature. Multiply them all, and I'm going to say in the paper is by foil. So what I'm trying to say is that the algebra is like 1 step.
Okay, okay.
It's
great.
1 step, really.
Very nice. Okay.
It's like, and here's another. It's another corollary that we ended up with. Suppose you have I'm sorry. I believe there was, so this is incorrectly stated. I believe there was a restriction coming in here, and I wanted to say that there are more. I forgot to write here the restriction. I forgot it right on the top of my head. This inequality was built on an inequality produced by Darius Greenberg. I did the same thing as in the IMO problem. I look at it and interpret it in function of the curvature invariants. And what I'm saying is that this is really There can be many. I'm not aiming anymore to classify them and put them in a table and so on. No, in classes. I'm interested in classes of inequalities. Now, let's take a look at another class of objects, the cat spaces. What's that? The terminology of cat spaces was coined by Mikhail Gromov. That's the acronym of the names of Cartan, Alexandrov, and Toponogov. It refers to a Riemannian manifold with sectional curvature bounded above by epsilon. What can you prove about those? Something similar with the Bonnet condition by going backwards. So suppose you have a cat space. So I'm looking at if this cat space can be viewed as a hypersurface dimension 3 that could be embedded into R4. And can we obtain anything about minimality? Is this a possible way to go? Let's see. So the condition looks like this. If you have epsilon more than the sectional curvature, then what you could do is to write these polynomials, FOIL patiently. As you can see, your degree 3 pops up naturally. No problem, and you're done. Why is this interesting? If you have a minimal embedding, then you have an inequality that functions as an obstruction to minimality.
No color.
Functioning as obstruction to minimality and involving this time this weak curvature invariant, which is the scalar curvature. And actually, it could be negative and still provide an obstruction to minimality. Okay?
No, that's very interesting.
So I don't know, it's very easy to reach, really. What did I do? Foiling. That was right there. So the philosophy is this. You're looking at some natural geometric conditions on the curvature and you're generating the corresponding inequality and then distinguish the classes of invariants. Some of them, they can be mixed. And it's very hard to retrieve any sort of information from them. I don't like those. But sometimes you can isolate the terms and you can come up with a geometric conclusion, and this is it. Aha, good, good, good. So, finally, that's why I bothered you in the middle of the summer to tell you the following conclusion. We have the following 3 classes of inequalities. First, you could have classes between intrinsic versus intrinsic, and you're going to say, oh, but this is not like what Xing and Chern was saying, but you could go into the ambient space and use your understanding from there, using the second fundamental form, to prove something about intrinsic behavior. That's really Nash's hope. Can I come back next fall and give you at least one example of such, because I have a trick that doesn't work, and it doesn't fit in today's story, but so to be continued, I have it. Intrinsic versus extrinsic, out of which the most valuable are the Bogdan type inequalities that you have seen, where infimum and supremum accordingly are obtained. And you could also have inequalities about extrinsic versus extrinsic, and the question is how much geometry is into that. Can they still characterize the immersions? And even more, can you say something in terms of extrinsic quantities that would force certain conclusions about the topology of the submanifolds? Yeah, it can be done too. So there is more here. Aha, that's the classification. This is how we should be thinking. Now, let's go back to, I'm going to try to conclude in a few minutes, because during the pandemic, we had a conversation about an inequality that I couldn't obtain properly and so on. If you remember, I was bothering you about it, and I'll get to it. Not before I'm going to mention that you can take a look at the, so you are on a hypersurface and you have those eigenvalues, lambda 1 to lambda n. How about you're looking at the difference between the highest and the smallest? That's the spread of a matrix. In this case, it's the spread of the shape operator. That's a curvature invariant. That's extrinsic. That's extrinsic because there is no way you can control it through. Now, there is a lot of stuff known, and I'm not going to go through the detail, but there is a lot of theory coming from linear algebra done in the, starting with the 30s. And a lot of inequalities about the behavior of matrices. Another problem that we looked at is if we can find a lower bound for the spread of the shape operator for a hypersurface in Euclidean ambient space. Now, the problem of the behavior in the neighborhood of the umbilicus is related to Kara-Theodori conjecture, and that's a very serious problem. Here we're just approaching it with some invariants, and it's really in the neighborhood of a very difficult challenge for us all. Do we have any lower bound for SA? Yes, we do. The very natural one coming from the linear algebra of Hermitian matrices. Shape operator is symmetric. So back again, we're dealing with the mean curvature and the Gauss-Kronecker curvature, and the shape operator will be lambda n minus lambda 1 if we order the eigenvalues in, let's say, alphabetical order. Can we say that? Now, who's this omega? This omega is a very extrinsic quantity that has to do with the very nature of the shape operator. So what is known from the classical theory, it's an upper bound. What we proved about a decade ago with a group of students that I believe you have seen speaking about it is this inequality. Now, let's say it clearly, this is an inequality between extrinsic quantities. That's an example of the third class. Because I didn't have any example of, I was like, how does it look? How do they look? They look like this. And it was a little bit of an industry of how to calculate that. Actually, the first inequality was the battlefield for us, because we had to do a splitting and we had to do a lot of algebra, and it was quite technical, right? And by building on this, I was able to calculate this limit. If this limit between the spread of the shape operator and this quantity inspired from omega, right, in the neighborhood of an umbilic, really, then if this limit exists, it lies necessarily there. This is what the double inequalities are telling us. Again, it's very technical. I'm not going to get into it. It's
And you also get the bounds.
yeah, you get some bounds, and I think we should be looking at these limiting processes in the neighborhood of an umbilic. That's, again, it's coming from far, this way of thinking. But what I was promising you, Mihail, and thank you very much for our conversations over the last 3 years, 4 years, okay, is the following, that you can actually come up with an inequality having Chen's delta invariant in the left-hand side term. And what you got in the right-hand side term is the spread of the shape operator. That's what I wanted, okay? And that's really
The first term, right? The first, or the whole thing, from the right-hand side.
Yeah, what I wanted is, I wanted a Chen type inequality involving the spread of the shape operator to be viewed as a useful, perhaps. Yeah. Anyway, it was easy. I didn't know how to do it, to be like whatever.
Okay.
And the conversation we had right before this talk was like, why didn't I have this in my thesis? Why didn't I do that 20 years ago or so? I didn't know how to think. Really. Okay, so for a smooth hypersurface, this is Chen's inequality. Just glue it together with the estimates you had, and done. No problem. That's not difficult. It's just a setup. You have to learn how to look at this carefully. And in terms of the normalized scalar curvature, you can have a corresponding inequality built on the one proved originally in '99. Yep, the same paper, and that's what I wanted to tell you. So there are actually 3 classes of inequalities, and we should be able to illustrate each one of them accordingly. And that's actually in the consequences of the Riemannian study of Nash's embedding theorem.
Thank you. Thank you.
Yeah.
Thanks from the Zoom audience as well.
Any complaints? I'm interested in complaints.
So Bogdan is interested in complaints. Any complaints from
Except the speed.
Jess or Jose?
I know. I'm aware what I did, but it had to fit. It had to fit.
Okay, now Jess was going back to the problem about the a plus b plus c equals 1, that you can prove it with Lagrange multipliers, and he's going to put it on the 210 midterm to see if there are any complaints. But he has no complaints about the talk. He's just, okay.
So
Thank you, Jess.
Yes.
Yeah.
So I'm sure Professor Euler would be pleased because he invented the method.
So for all these groups, right, of inequalities,
Yeah.
probably, I mean, I'm asking. There are special cases when you get exactly equality, and those
Yes.
are trivial or non-trivial?
Highly non-trivial. Okay, this is actually that's the way to think, because the equality cases are those best embeddings according to the K-tuple, according to K-tuple. So this is like the ideal embedding.
And they're highly non-trivial. They're not.
The high
flat
non-trivial, the
things.
important, okay, the important inequalities are those ones that are actually emphasizing subspaces satisfying the equality case.
Right.
If you can come up with an inequality that emphasizes a class of objects that was never studied before, that would be valuable.
Right. Okay. Great. Yeah.
So that this is what we're in. I mean, you're investigating the best possible embedding according to one of the inequalities that are capturing the geometry of the subspace.
Yeah. Okay. Yeah.
Sorry, I forgot to say that.
No,
Technical
that's fine,
is,
that's
is too important. Because what we did here is there are some functionals about curvature and they should have some equilibrium situation. The equality
The
cases.
examples are highly non-trivial, of course.
When you control, so
They should be.
for Chen's equalities, you have a characterization. So at the point of the subspace, there exists a basis on which the shape operator can be written in a certain form. You control it that way. But let's say, to go into on the real examples in the most general case, that's a very difficult.
It's very difficult. Because most of the examples are like,
Yeah.
No, that's great. Okay. Oh, leaves a lot of work from all.
That's what I'm saying.
Yes.
There's a homework for everybody. Are there any more? What are we doing here? Now that we have this way of thinking, this is more like a way of thinking for classes of inequalities.
No, great. That was a great talk. Thank you.
Thank you.
Yay.
Let me drop the mic.
Sorry?
Drop the mic.
Yes, okay, so I'm going to stop the recording. Okay, everybody.